Hello and welcome back. In this video, we'll be looking at u-substitution. And essentially, u-substitution helps us take antiderivatives of slightly more complex functions. Specifically, if we have to use the chain rule to take the derivative of a function, you would use substitution to take the antiderivative to get back to the original function. So let's take an example here. I've got the derivative d by dx of 3x squared plus 4 all raised to the 5th power. So we can see that we have our inside function being raised to the 5th power. So with the chain rule, what we do is we treat this like anything raised to the 5th power. The derivative is going to be bring down the 5 and raise it to the 4th power. Plus, we have to remember to take this times the derivative of the inside of the function. And then the derivative of 3x squared plus 4 is going to be, so we'll have 3 times the derivative of x squared, which is 2x, so that will be 6x, and the derivative of 4 is 0. So this is going to be our derivative, and you'll notice that, okay, so we have the part out front that is simply the derivative of anything raised to the 5th power. We bring down the 5 and raise it to the 4th power. And then we take it times the derivative of the inside. And the derivative of the inside of this is going to be 6x. Now, when we look at taking the antiderivative of this guy, we know that the antiderivative of a derivative, they undo one another. We would just get back our original function. So the antiderivative of 3x squared plus 4 to the 4th power times 6x, we know that this is going to be 3x squared plus 4 all raised to the 5th power plus c. We can't forget our plus c, because if there was an extra constant in here, it would just disappear when we took the derivative. So here we have our formula for this. We know that the antiderivative of this function is going to be our original function plus c. But the question is, if you were to stare at this long enough, how could you possibly tell that this was going to be your antiderivative? And I think the helpful thing that I can point out here is what we'll do is we'll make a substitution. So I'm going to let u be equal to 3x squared plus 4. And if I substitute this in, what do I get? This is going to be the integral of 5 times u to the 4th power. I've got the 6x hanging around, so I'm just going to leave that there for a moment, times dx. And then we have, so we almost have an integral in u. And it turns out that this part to the side is going to be the same thing as du. And this is a function that we can take the integral of. 5 times u to the 4th power. We raise u to the 1 higher power, and we end up dividing by that power. And 5 divided by 5 is just 1. And maybe we'll just leave that there. But then if I take u to the 5th power, that's just going to be 3x squared plus 4 to the 5th power. When I turn this inside function into a u, if you integrate u to the 4th power, we get u to the 5th power divided by 5. And if I remember my plus c, we get exactly the right answer. So I think the hardest part about all of this isn't necessarily recognizing, oh, I can turn this into a u. It's this part at the back. And this is what's called a differential. And there really isn't anything to this. It's not very complicated. But a differential is what this dx is called. And to find a differential, it's pretty easy. If dy dx, if the derivative of y is the derivative of this function f of x, then dy itself is just going to be that derivative times dx. What it looks like is I'm multiplying both sides by dx. This is technically not the case. In mathematics, the dy dx can't be separated in the sense that the dy and dx aren't their own things, so we can't multiply both sides by dx. But that's really what it looks like, and for the purposes of this class, we can just treat it as such. So we'll just move the dx to the other side, and dy is going to be the derivative of f times dx. So let's do a couple of examples like this. Let's find du if u is equal to x cubed. So what we can do is we can find the derivative of u with respect to x. So this is going to be the derivative of x cubed. And the derivative of x cubed is going to be 3x squared. Again, raise it to the 1 less power and pull down the exponent. So this means that du is going to be 3x squared dx. And that's it. So I can find this differential by taking a derivative and plugging a dx at the end. And this is how we will know how to substitute this last part of our integral. Let's do a couple more examples with differentials. Here, let's find du if u is equal to e to the x. Well, what I need to do is find the derivative of u, which I'm finding the derivative of e to the x. And e to the x is one of our special functions because e to the x is its own derivative. So here, the differential of u, du, is just going to be e to the x dx. And that's it. And let's do one final example. Let's say u is equal to x cubed plus 5x squared. So then let's find the derivative of u. So du dx is going to be the derivative of x cubed plus 5x squared. And again, we'll just take the derivative of each one of these and add them together. So the derivative of x cubed is going to be 3x squared. Bring down the 3, raise it to the 1 less power. Plus, this will be 5 times the derivative of x squared, which is going to be 2x. Again, bring down the 2, raise it to the 1 less power. And we can simplify this guy to be 10x. Cool, so this is our derivative. So the differential, du, is then going to be that guy times dx. And there you go. So now we can find differentials. How do we use this? We're going to use this when we make substitutions into our integrals. So here I've got the integral of f of x times f prime of x, the derivative of f, with our differential dx at the end. And I'm going to say that this is actually going to be the integral of u du. So how do I do this? Well, I've got f of x out front. So what I'm going to do is we're going to say let u be the same thing as f of x. So what I'm going to do is I'm going to substitute u in for f of x in here. So the derivative of f of x, f prime of x, dx. Well, if u is equal to fx, I can substitute that in. But I don't want to take the integral of something with a u in it with respect to x. This part at the back, I don't want to have any x's left. Well, if u is equal to f of x, this means du is going to be our differential, the derivative of f times dx. So then I can replace this f prime of x dx with du. And there you have it. I can turn the antiderivative, or the integral of something that looks a little bit complicated into something that's a lot less complicated. And I think the best way to see this is using some examples. So when we are looking at the integral of 4x plus 10 to the third power, this is again a little bit complicated because it looks like I've got a function inside of a function, so we might expect like a chain rule to pop out. So this is how I know to use u-substitution. It looks like a chain rule, but we're taking an antiderivative. So we're not going to use the chain rule, that's for taking derivatives. We use u-substitution for antiderivatives. So we need to find a function to replace with u. And what I'm going to do is I'm going to take the inside function. And we're going to let u be equal to 4x plus 10. And right away, if I make that substitution, if 4x plus 10 is going to be u, I'm going to be integrating u to the third power, but with dx out here. I don't want dx, I want du. I don't want to take the integral of u with respect to x, I want to take the integral of u with respect to u. I want du out here. So I need to find du. And again, du is just going to be the derivative of this guy with a dx. So the derivative of 4x plus 10, the derivative of the 4x part is just going to be 4. The derivative of the 10 part is just going to be 0 dx. So I need to get rid of this dx here. So if I solve this guy for dx, dx is going to be du divided by 4. So I can make that substitution in here. This is going to be the integral of u cubed. This dx is just du divided by 4. And now I do want to rearrange this just a little bit because it's a bit more helpful. This is going to be the integral of 1/4 u to the third power du. And this is something that we can take the antiderivative of. So again, I can pull constants out of antiderivatives, and then the antiderivative of u to the third power is going to be u to the fourth power divided by 4. Again, we raise it to the one higher power and we divide by that power. So when all is said and done, we get 1/16 u to the fourth power. And the question is, are we done? Well, it looks like it. We've taken an antiderivative, but our initial antiderivative is in terms of x, and what we have here isn't in terms of x. So we'll make one final substitution. I'm just going to plug in what I know u is in terms of x. So I get 1/16 4x plus 10 to the fourth power. And that is an example of how we use u-substitution to find an antiderivative. But I nearly forgot my plus c. Always important if we don't have bounds on our integral.